Want to go ahead and welcome everyone. Our speaker today is Steve Wright. I don't think Steve really needs that much of an introduction in our department, but for students who are just sort of starting and getting familiar with the topic, Steve's really a singular figure in optimization. He's written sort of the standard text on numerical optimization, interior point methods. He most recently won the Kachin Award. I don't know if I'm saying that correctly, but I'm trying my best. From the Informs Optimization Society, and he's sort of been tirelessly serving this community for many years now. If you look back to see his editorship roles at Math Programming and SciOpt are sort of top journals. But more than this, the thing I really appreciate about Steve is, and what is maybe most unique about him is how generous he is with his time, especially with young people. And I saw this a lot, especially when we visited Simon's a couple of years back, which was fun, myself included. And in some sense, I have to credit my career to Steve this far, since without his recommendation of Zantac to me a few years back, I would not have been able to drink as much coffee as I had to complete my job. So thanks, Steve, for introducing me to Zantac, and special thanks to Zantac for sponsoring this talk. I guess I don't know what the title of your talk is right now, so I can't read it, but
that's okay.
Fantastic.
Well, thank you. That's a very, very generous and unique introduction, Damek. Thank you for that. So it's really a delight to talk at Cornell. I used to visit quite often, but mostly back in the 90s. And I think my last visit was for Mike Todd's retirement event, which must be 5 or 6 years ago now, which I greatly enjoyed. I hope at some point to visit again, and you guys owe me a dinner, I think, because I feel like I'm doing, I feel like I'm really there except for the fun dinner. So maybe we can make up for that next time. So it's a pleasure to talk about some stuff that I've done over the last 3 years or so on sort of equipping standard optimization methods, both constrained and unconstrained, with some worst case complexity guarantees, and with an emphasis on the non-convex case, and also an emphasis on trying to find approximate second order points. So there's quite a bit of material here, so I'll have to go through it at a fair pace, but please feel free to just unmute yourself and ask questions if you have anything. So I'll first give some motivation, then I'll talk about some methods we devised in the unconstrained setting, line search methods, recently completed paper on truss region methods, and then some work we did on problems with strict saddle points, for which we can prove vastly better complexity results. Then I'll say a little bit about stuff we did for the bound constraint case, which is kind of the simplest inequality constraint case. We have a log barrier method, and then recently there's work in progress on a projected Newton CG approach. And finally, I'll talk a little bit about an approach for equality constraint optimization. And ultimately, we'll get some results for the inequality constraint case by combining the last two, the bound constraint and the equality constraint case. So this is joint work with several colleagues, Frank and Daniel at Lehigh, UA, who's my postdoc at Wisconsin, Mike O'Neill, who was my student. He graduated in the summer and he's now a postdoc with Frank and Daniel at Lehigh, and Clément, who was my postdoc here at Madison, and he's now a faculty member in Paris. So complexity, the idea of complexity is to try to find a bound on the amount of computation for an algorithm and or a problem in a certain class. And I think probably all of you on this talk have an idea of what that term means. But one interesting thing is, how do you measure the amount of computation? And there's a few different ways of doing that. One is to just count up the number of iterations in the algorithm. Quite often you've got multiple levels of iteration, and so you might want to count up, for example, the total iteration count, which might be the total number of inner iterations that you need. Another way of measuring it is to define some fundamental operation that your algorithm has to perform, like evaluating a gradient or evaluating a function. So this is the notion of oracle complexity. And you try to get an upper bound on how many times you need to invoke the oracle before you can find an approximate solution that's accurate to some extent. So in this talk, I'll talk mostly about upper bounds on the amounts of computation. There's also a lot of interest in finding lower bounds, but I won't I won't say anything about that. Probably quite a few of you know, I know some of you I know for sure know this fundamental text of Nemirovsky and Yudin from, I think the English translation was 1983. I think the Russian version is a few years before that. But that's sort of a founding document when it comes to analyzing the complexity of continuous optimization methods. And in the very early chapters of this book, they sort of define exactly what they mean. They talk about three ingredients as being essential to complexity. One is identifying the class of problems that you're trying to solve. The second is sort of defining what the oracle is. What are your sources of information about the problem that you can interrogate in order to make your algorithm work? So it could be just evaluating a function, it could be evaluating a function and a gradient at a given point X. And then the third important ingredient was defining what you mean by an approximate solution. So quantifying the level of accuracy in the solution that you find. And so this can be defined by, so for example, some parameter epsilon. And so it could be that you define the complexity in terms of how many iterations you have to take, how many of these elementary oracle calls you have to make in order to get the level of approximation down to some specified level epsilon. So in this book, they focus mostly on convex problems. They sort of throw up their hands in the first chapter and say, look, we know that in general, if you've got a non-convex function and you're looking for the global minimum, that's just exponential in the dimension. There's pretty much nothing we can do about that. So for the rest of the book, they just really focus on the convex case. And there was, of course, a lot of interest in complexity results in convex optimization, particularly during the interior point gold rush in the 80s and 90s. It was kind of an essential ingredient whenever you're writing a new paper for interior point LP or LCP or semi-definite programming, you'd prove a complexity result, a worst case result. That was kind of de rigueur back in those days. Nesterov, of course, for these momentum type methods for nonlinear convex optimization, like Nesterov's accelerated gradient, heavy ball, and so on, there was interest in the worst case complexity of those results all along, going back to the early 80s and even into the 70s for that case. And then classical analyses of stochastic subgradient and subgradient methods, they also come usually equipped with some sort of worst case convexity result, either for the iterates themselves or for the averaged iterates, some sort of weighted average of all the iterates that you've seen. So in the non-convex case, though, the interest, I would say, is more recent in equipping these with complexity theory. And the focus has been not on finding global optima, which are still sort of too hard in general, but on finding approximate second order points, which I'll define in the next few slides. So in other words, can you give me an upper bound on the amount of work I need to do to find a point that approximately satisfies second order optimality conditions? And so what's the motivation for this? Well, one is that, you know, it is sort of interesting to have these guarantees. Maybe you might even sort of get some enhancements to practical methods. But I think one real driver here of the interest is that in a lot of interesting applications in machine learning, particularly those involving matrix optimization, finding an approximate second order point is enough, because these points are either global minima, or you can say they're sort of morally equivalent to global minima. And another reason is that all saddle points are strict. There are certain problems particularly in the matrix optimization space, where a point, if it's a saddle point, there's a well-defined direction of negative curvature, which will let you escape from the saddle point. So if you can find a point where the second order conditions hold, you've essentially found a global minimum. And so there's sort of more than meets the eye to these approximate second order points. In the machine learning setting, it's sort of equivalent to finding a global minimum. So the philosophy that sort of I like to approach this whole area from is, I sort of recognize that over the last 50 years, people have developed a very rich collection of practical algorithms for nonlinear, non-convex optimization, both unconstrained, bound constrained, general nonlinear constraints. And rather than sort of invent new methods that have good complexity guarantees, my preference is to sort of build on these classical methods, maybe add some bells and whistles, some additional checks and so on, so that you can equip them with worst case complexity guarantees without sacrificing too much their nice practical properties. And so that's my take on this area. Other people have sort of approached it differently, where they've sort of invented new methods from the whole cloth that have nice complexity guarantees, but these new methods may not be terribly interesting from a practical point of view. So that's my approach. I'm particularly interested in ones that come with approximate second order guarantees rather than just finding approximate stationary points. And the other take I have on this is that I don't like to force you to evaluate the Hessian or second derivative information and explicitly work with it. I sort of assume that all we're allowed to do with the Hessian is to form matrix vector products involving the Hessian. So in other words, all I assume here is that at a given point X, I've got to be able to form the product of the Hessian with a vector D for any given D, okay? And so the only way I can access the Hessian is through matrix vector products. And the reason that's interesting is that you can provably do that in an efficient way by applying computational differentiation to the inner product of the gradient with D. So you can boot up, if you do a web search on computational differentiation or read the book of Grivak and Walter, you can get more details on how to do that. But you can provably do that without actually knowing the Hessian or ever evaluating it explicitly. Just all you need to know is how to evaluate the gradient and then how to call a computational differentiation package. So that's how I access the Hessian. Okay, so let me start by talking about what we do in the case of non-convex constrained optimization. When should I aim to finish up, by the way, Damek?
We started a few minutes late, so about 5:19, I guess, around then.
Okay, yeah, that's plenty of time. Yeah, thanks. Okay, so let's talk about the case where you've got, you're trying to minimize the function f. I'm going to assume that the Hessian's are Lipschitz continuous here. So it's quite a smooth function. I'm also going to assume that it's bounded below by some number f low that you don't know. You just know that f low exists. And right away, you can bound with the knowledge that the Hessians and the gradients are Lipschitz continuous with constants LH and LG. Right away, you can write down quadratic and cubic upper bounds on the value of f at a point x plus p by using function, gradient, and Hessian information at x. And this is just, extension of Taylor series type arguments. You can write down these simple quadratic and cubic upper bounds. And these turn out to play really crucial roles in the analyses. So what we're looking for here is an approximate second order point. And by that, I mean that I need to get the gradient below, the norm of the gradient below some specified tolerance epsilon g. And I need to find a point where the eigenvalues of the Hessian are all bigger than minus epsilon h, where that's another small specified tolerance. And I'm going to be looking for the iteration complexities of finding these points. How many iterations of this method am I going to need to come across a point that satisfies both of these properties simultaneously? And also I'm going to come up with some a measure of operation complexity. So this is a kind of oracle complexity. So in order to do that, I need to tell you what the fundamental operation is that I'm going to be measuring the operation count by. And my fundamental operation is going to be either evaluation of a gradient or evaluation of a Hessian vector product. And both of those things I sort of put in an equivalence class. And I sort of say, that's my fundamental operation. I'm going to assume that the evaluation of the function value is cheaper than that. Okay. So that's reasonable because if you evaluate the Hessian vector product by applying computational differentiation to the inner product of the gradient with D, it only costs a factor of 3 or 4 times more to get the Hessian vector product. So there is actually a solid rationale for putting these two things, gradient evaluations and Hessian vector products, in the same equivalence class when it comes to measuring the oracle. So that's my justification for that. So I'm going to have two kinds of complexity, just counting up the number of iterations, telling you how many iterations I need to find one of these approximate second order points as a function of epsilon g and epsilon h, and then also telling you how many of these operations I need, again, as a function of epsilon g and epsilon h, to find a point satisfying both of those properties at once. Okay, so to sort of set the scene, I always like to present this algorithm. In my group, we always call this the stupid algorithm. Here I'll call it the basic algorithm. But there's a very simple algorithm that sort of illustrates the ideas of the flavor of analysis that we use in order to get these results. So this is a very simple algorithm for minimizing f that takes two kinds of steps. First of all, if the first order condition is violated, if the norm of the gradient is bigger than epsilon g, we simply take a short step, steepest descent step. We just move at a distance 1 over lg in the negative gradient direction. And by plugging that into this quadratic upper bound that I showed you on this earlier slide, it's very easy to show that the function is going to decrease by at least this much. So you're guaranteed in going from xk to xk plus 1, you're guaranteed to decrease the function by at least an order epsilon g squared amount, okay, if you take that step. Okay, so that's the first kind of step. But if it turns out that you are below threshold, if your gradient norm is already smaller than epsilon g, we're going to take a different kind of step, and that is we're going to find the direction of most negative curvature for the Hessian. And if that direction of most negative curvature has curvature less than minus epsilon h, we're violating the second condition here. And so we're going to take a short step in the direction of decay. And it turns out that you can show that if you take that step length, 2 times the absolute value of the minimum eigenvalue divided by the Lipschitz constant for the Hessian, you can show by just plugging into this cubic upper bound, this one here, that you're guaranteed to get at least this much improvement in going from xk to xk plus 1, okay? So in other words, if at least one of these two conditions is violated, you can show that you get either this much decrease or this much decrease in f, okay? So now you can really just put those two things together. You've got a certain amount of guaranteed decrease at every iteration. You know that there's a lower bound on the function, okay? So if you just divide the distance between your initial function value and the lower bound, divide that by the amount of improvement that you're guaranteed to make at every iteration, that immediately gives you an upper bound on how many steps you're going to need. And it's just the order of epsilon g to the minus 2, epsilon h to the minus 3, with some Lipschitz constants in there as well, which we're going to ignore. We're just going to focus on the dependence of epsilon here, as in the original Nemirovsky-Uden book. So this is, a very simple algorithm with a very simple way of deriving the iteration complexity. So how do we turn that into an operation complexity? Well, the way that I've written the algorithm here, we've got this big operation, which is find the direction of most negative curvature. So, given that I'm only allowed to do gradient evaluations and Hessian vector products, how do I express that in terms of those fundamental operations? Well, it turns out you can do randomly started Lanchos and apply that to this Hessian, and you can show that at the cost of order epsilon g to the minus 1/2, you can find the most negative eigenvalue to an accuracy of epsilon h. So it turns out you don't actually need to find the most negative curvature direction. You just need to find a negative curvature direction whose curvature is less than minus epsilon h. And it turns out you can do that in this much work. And so that's the internal cost of basically of the second kind of step. So if you factor that into if you multiply that internal cost by this iteration complexity, you get an operation complexity, which is a factor of order epsilon h to the minus 1/2 greater than this iteration complexity. And so for this very simple algorithm, we can get not only an iteration complexity, but also an operation complexity. So I said that interest in this kind of these kinds of methods doesn't go back all that far. There's this very important sort of foundational paper by Nesterov and Polyak from 2006 that really sparked a lot of interest in these kinds of methods, and it made use of this cubic upper bound, the same one that I showed you on the earlier slide, except that they don't assume that you know what that Lipschitz constant for the Hessian is. They sort of try to find that adaptively, replacing that by this constant m. But this idea of using cubic regularization, interestingly, it goes way back. Grievant told me about this in 1986. He'd written a tech report in 1981 that had basically proposed using this kind of way of evaluating a step, and it never got published. He got referee reports on it, which actually weren't too bad. And he tried to talk me in 1986 into helping him revise the paper and putting my name on it. Unfortunately, I never took him up on this because it's been recognized as posthumously as kind of an important work. It turned out that Curtis, Gould, and Twant sort of came up with this idea in about the late 2000s as well, with a similar idea, and have continued to publish works on this over the last 12 years or so. So there's a list of papers here. A number of other people have done stuff on this. Karcher has also worked on this, particularly in the context of using inexact gradient and Hessian information and inexact models for finding the step. So there's this very nice paper of Korakadis and Karcher where they show that you can basically recover the deterministic complexity results even with these inexact function values to within some reasonable constant. And then recently, Curtis, Gould, and Twant have tried to extend these ideas to finding points that satisfy necessary conditions higher than second order. Now, most of these results are for iteration complexities, but also there's been some work on finding operation complexities as well. That's fairly recent. That dates to about 2016 or so. People have done work here sort of using sort of methods that make use of accelerated gradient ideas, convexification, cubic regularization, truss region, and so on. There's also this line of work by Shi Jin and Michael Jordan and Netropali and Shamka Carter and so on, where they just use gradient with occasional injection of noise to escape from saddle points. All of these papers sort of come up with bounds on the number of fundamental operations such as Hessian vector products or gradient evaluations that you need to find approximate second order points. So there's been quite a lot of activity in this space in the last few years. So what do we do? So we have this method that sort of improves on this stupid method. It's able to decrease, essentially the improvement it gets is to decrease this epsilon g to the minus 2 and improves it to an epsilon g to the minus 3 over 2, which sounds like a minor improvement, but it's sort of surprisingly hard work to just make that advance. But our idea, we claim, is a pretty practical idea. It's sort of based on a classical Newton CG procedure, which has been an idea that's been around for about 20 years as a practical method. The idea is you essentially take Newton steps, but you calculate the Newton steps by using conjugate gradient. And if the conjugate gradient indicates to you that the Hessian that you're working with is not positive definite, then you do something else, like take a negative gradient step or something like that. So that's our starting point, and we sort of enhance that by, first of all, adding a damping term to the Hessian for reasons that are mostly technical. This sort of helps us in discovering where there's a direction of sufficient negative curvature along which we can make progress. So it helps to kind of shift all the eigenvalues of the Hessian up by epsilon h, because then if the conjugate gradient bombs out, we know that if the conjugate gradient is detected in negative curvature direction, it's a direction of decently negative curvature along which we can expect to make significant progress in the step. But this is our idea. We generate steps like this to a slightly damped Newton system. If CG, we try to make sure that CG doesn't run too long, because that's going to destroy our operation complexity if CG is going to need a full n iterations to converge. So we have to put all sorts of safeguards inside CG to make sure that it doesn't take any more than epsilon g to the minus 1/2 iterations. There's always a chance that CG will fail, a so-called hard case, where the negative gradient doesn't pick up any of the subspace corresponding to the most negative eigenvalue in the Hessian. And so we sort of have to have this extra step where we think we're at a solution, but we call randomized Lanchos just to make sure that we're not missing out on detecting negative curvature in the Hessian. So that's sort of this final check sort of step that we have to include in the algorithm to make it all work. So, you know, the CG step for solving this damped Newton system looks like this. And the reason for showing you this is not to sort of educate you on what CG does, but just to point out that the majority of this is just bog standard conjugate gradient that you'd find out from looking any textbook about conjugate gradient. So all those black lines are just the standard conjugate gradient approach for solving a positive definite linear system, but there are enhancements in here. So everything red are sort of things that we have to do to, first of all, detect negative curvature, and secondly, to make sure that CG isn't using up too many iterations and messing up our operation complexity. So the key is that we have to apply 4 termination tests. And the first one is just the standard test that you apply when everything seems to be positive definite and all you're interested in is finding a solution of sufficient accuracy that the Newton step will give you a reasonable decrease. So that first condition is the sort of classical approximate damped Newton step condition. The other 3 conditions are the safeguards you need to sort of stop you from iterating too long, and also to check that the matrix that you're working with really is positive definite. So in other words, a negative curvature detection thing. So 2 of the termination tests, basically they're detecting whether either the step or the current iterate seems to be a direction of negative curvature for the Hessian. And if it is, that's sort of good, because not only is it, if it's a direction of negative curvature for H bar, because H bar is a shifted version of H, that's telling you that you've actually got a direction of decently negative curvature for H itself. And so it's a useful direction to move along. The last termination test is actually a much more sophisticated one. And basically, it's a way of checking that if you're taking too many iterations, if the convergence of CG is too slow, it's an indication that lurking somewhere in the background is a negative eigenvalue. Even though you haven't explicitly encountered it yet, slow convergence is an indication that that's a negative eigenvalue there somewhere. And it's based on an argument actually of Bubeck, and it's quite a sophisticated one. We had to modify it to make it work for CG. They did in the context of accelerated gradient, but it's a way of recovering a direction of negative curvature from observing slow convergence in CG. So the last ingredient we need to apply, as I mentioned earlier, is that you sort of have to do this final check by calling randomized Lanchos, just to make sure that CG hasn't missed out on finding a negative curvature direction, because it could be that the negative gradient doesn't lie in a subspace that includes the negative curvature directions. So you sort of have to resolve, run a randomized Lanchos process just to double check. And this just goes back to using some papers by these 2 authors from the early 90s, where they analyzed randomized Lanchos and they got convergence rates for converging to the extreme eigenvalues. So please stop me and ask if you have any questions anywhere here. So this is the overall approach, and it's basically, I won't go through this in detail, but it's basically, as I said, if your gradient is too big at the current point, if it violates the first order condition, you solve this approximate, you look for this approximate Newton step. If during the process of applying CG you found a negative curvature direction, then you use that as the search direction. Otherwise, you use the damped Newton step as the search direction. If, on the other hand, your gradient was small, you seem to be at a stationary point, you call the randomized Lanchos to explicitly look for a negative gradient, a negative curvature direction, and use that as a search direction. Either way, you do a backtracking line search. You could, of course, do something fancier, but this was good enough from a complexity point of view, and it's also, reasonably practical. You just do a backtracking line search until you satisfy a cubic decrease condition. So what we end up with is that the iteration, this is the last sort of ingredient. We do all the analysis in terms of using a different tolerance for the for the Hessian from the gradient, for going right back here. But in the end, in order to make things sort of convenient, we tie the epsilon g and epsilon h together by assuming that the epsilon h is the square root of the epsilon g. And so we do everything in terms of just the epsilon g in the end. This seems to be what everyone does. There's not a really fantastic reason for doing it this way, but essentially one reason for it is that you've sort of got the min of two terms in the complexity bound. And if you make this identification between the two epsilons, those two terms end up being the same thing. So that's, as good a justification as I can give. But if you make that identification, we end up with an iteration complexity of epsilon g to the minus 3/2 and an operation complexity of order epsilon g to the minus 7/4. I should have said here that whenever you do this randomized Lanchos, there's always a possibility that it will fail, because you might start from a right-hand side, the randomly generated right-hand side might lie in a really nasty subspace. So there is some tiny possibility that it will fail. But that possibility only enters logarithmically into the complexity bound, so it's not particularly significant in the end. Okay, and I should mention that these results sort of mesh with the best known complexity results that were found by these other authors starting in about 2016. But we claim our algorithm is, a little bit closer to being practical. It's sort of closer to a classical optimization method than those other methods are.
Okay. Steve, just a quick question about that.
Sure.
So the algorithms you're talking about, are they the ones by like Alan Jew and others, or?
Right.
Yeah. Okay.
Yeah.
What kind of algorithms are those? I remember they involve some sort of randomization, I think.
Yeah, they do different things. Some of them do use this randomized Lanchos idea, but for example, the one by Carmen Aducci and Sidford, and I'm forgetting the fourth author, I'm really sorry. But that one sort of it doesn't use conjugate gradient, it uses accelerated gradient. And they basically add on a big convexification term to make accelerated gradient work. Mm-hmm. And they've sort of got ways of detecting when they're actually dealing with I think they figure out how big the convexification term needs to be by running randomized Lanchos and getting an estimate of the most negative eigenvalue and devices like that. But it's not a terribly practical method, I would say. They've got a successor to that called convex till proven guilty, where they run randomized Lanchos until it comes across a negative curvature direction, and then they sort of step along that direction and do something different. So a lot of devices like that. There's another one by Elad Hazan and his group, Brian Bullens, and some other authors. I think Alan Jew might have been on this one, where they come up with a method that's sort of a hybrid of the cubic regularization and the trust region idea. So there's a lot of different approaches, but ours is sort of close to something that was pioneered by Steihagen around 1980. This idea of using CG to calculate the Newton step, and then there was a bunch of papers by what was it? Steihagen, Twant had another one, and Dembo and Eisenstadt. Dembo, I guess, was a Canadian who went off to do finance after a while. There are all these papers that appeared in the early 80s on that topic. So ours is sort of close to that idea.
I see. And there's one follow-up. Is that so that's still the best known exponent for epsilon?
As far as I know, yeah. Epsilon g to the minus 7/4. A bunch of people got algorithms that all had that exponent. As far as we can tell, that's your best you can do for this kind of method that uses either first gradient information or Hessian vector products. Seems to be the best you can do. Okay, I guess the second thing, this paper has just been accepted to SciUp this week, actually. This is a trust region version of the same idea. And the reason we got interested in this is that this is joint with Frank and Daniel at Lehigh and Clermont also. It's sort of very similar to the line search method that I just talked about, but it's a little bit closer to what Steihagen did in his 1980 paper. So Steihagen's method was, he basically used the trust region idea, which is where you solve a problem of minimizing a quadratic model of f using second derivative information subject to a truss region. So the step is confined to lie in a ball. And again, it looks like here I'm using the Hessian again, but in fact, what Stihag does is apply CG to minimizing that function M, that model function. And in order to apply CG, you only need to know Hessian vector products. And so it sort of stays within the rules that I've set for myself here. But Stihag's algorithm, what he did is start from S equals 0. That was his initial guess. Apply CG. And if any of the CG iterates crossed over the truss region boundary, in other words, if the norm of S ever got bigger than delta K, then he would truncate the step at the boundary and return that as his approximation to the solution of the truss region subproblem. But if that never happened, if he could keep taking CG steps and never leave the truss region, then he would just keep going for n iterations until he actually achieved the solution of this subproblem. Also, if the CG ever encountered a negative curvature direction, it would do the same thing. It would move along that negative curvature direction until it hit the boundary of the truss region and then return that boundary point as the approximate solution. So that was his approach. It turns out that from this 1980 paper, it's been quite popular in practice. It's got some advantages in that you can prove at least convergence to a first order point. It converges to a stationary point. It doesn't have complexity guarantees from the simple fact that the CG itself might take n iterations, which is like too many for us. And there's no second order guarantees either. In other words, if you happen to land at a saddle point, this method won't move away from that saddle point. But anyway, it's a practical method, and we wanted to do something that was as close to this as possible, but something that we could prove this epsilon to the -7/4 convergence guarantee for. So it turns out that we didn't have to do too much. One thing we had to do was to damp this Hessian a little bit for the same reason as before, that we wanted, if the CG told us that that it found a negative curvature direction for the damped Hessian, we could translate that back into a significantly negative curvature direction for the original Hessian. So we had to do the damping there again. We had to use the same sort of enhanced conjugate gradient as we did for the line search method with these 4 different checks to look out for negative curvature and to also terminate when you got a residual that was sufficiently small without going all the way to the exact solution. And our algorithm also had to invoke this minimum eigenvalue oracle, this randomized Lanczos approach. In this case, we only had to do that typically at the very last iteration. It was sort of a sanity check just to make sure that we really were at a second order point. So the minimum eigenvalue randomized Lanczos only plays a pretty minor role in this truss region variant. So cutting to the chase here, I'm sort of skipping all of the details here, but I'm sort of giving you at least the basics of what we did. We can essentially prove the same sorts of complexity results, or almost exactly the same as in the line search case. And this time we went a little bit further, and well, we ran numerical tests for the line search case as well. But in the truss region paper, we went so far as to do some pretty exhaustive tests on the QTIS test set. We took all the larger problems from that test set with dimensions up to 1,000. We sort of programmed up our method and compared it to a bunch of other large-scale type truss region and Newton type methods. We made some choices for the damping parameters here, or the convergence tolerances, and we plotted. We did these Moray-Dolan type convergence plots to sort of log the practical performance of these methods. I'm not going to explain to you what these plots are. I'll just point out that the line corresponding to our method is the purple line, and you can't really see it here, but that's kind of the point. The point I'm trying to make is that we didn't really pay any price in terms of the number of iterations when compared to some of these other variants. And these other variants are things like variants where we don't damp the Hessian, and variants where we don't sort of cap the number of conjugate gradient iterations. So it doesn't seem to affect the number of iterations too greatly over these, traditional Stihag methods. When we drill down a little bit further and look at the number of Hessian vector products, it turns out that adding on these damping terms does make a bit of a difference. So these two lower lines here are the methods where we added a little bit of damping to the Hessian versus the ones that we don't. So that did sort of interfere with the number of Hessian vector products a little bit, but not dramatically. In the end, it wasn't like we were, getting dramatically worse performance. So the moral of the story was we got sort of pretty similar practical performance to the original methods, but we now have convergence. We now have complexity guarantees that we never had before. We got those without paying a very high price in terms of practical performance. So I want to talk a bit now about stuff that we submitted a few months ago, and this was part of Mike O'Neill's thesis. So now we went and said, well, let's look at a particular class of unconstrained problems, specifically low-rank matrix problems of the type that show up in machine learning. So these can be formulated as unconstrained, non-convex optimization problems, but they've got some additional properties, namely that all of their stationary points are either solutions or they're strict saddle points. And by strict saddle points, I mean points where there are directions of positive curvature, so directions along which the second derivatives have sort of positive eigenvalues, and other directions of negative curvature, where when you look at the Hessian at that stationary point, you can identify strictly negative eigenvalues. And so that's a nice property, because if you know that that's true, you've got a way of escaping from these saddle points, and your algorithm can get away by moving along those negative curvature directions. So we wanted to ask you, if you've got points with those kinds of guarantees, can you maybe give better complexity guarantees than the ones that you can just for general non-convex problems? And the answer is yes, otherwise I wouldn't be telling you about this, but they're sort of remarkably better results. So here are some examples of low-rank problems that show up in machine learning. There's a simple rank constraint problem where you're trying to minimize a smooth function f over the space of n by n matrices, where you want to constrain the rank to be R. There are matrix completion problems and matrix sensing problems where, again, you're looking for low rank solutions. So the way that people solved these problems originally was to add on a nuclear norm and a regularization term to try to enforce low rankness. But what people have been doing, what's become much more popular recently, is to use this Bureau-Montero idea of replacing that matrix with an explicit outer product of two skinny matrices U and V. So U and V are now n by R and m by R matrices, where R is typically much smaller than m or n. So you basically reformulate this problem. Rather than being f of x, you rewrite it as being f of uv transpose, where u and v transpose, I'm just going to stack them on top of each other and put them in a matrix W. And so I can think of this as being a non-convex problem in this variable W. Now, it turns out that by doing this, you're introducing a bit of ambiguity into the solution, because if I just post multiply u and v by the same R by R orthogonal matrix, UV transpose is not affected. And so there's kind of this scaling ambiguity, and you can resolve that by requiring U transpose U and V transpose V, both of those things are R by R matrices, by requiring those to be the same. So the problem that we actually solve in practice is to take this original objective, F, which for some reason I can't highlight anymore, and add on this scaling term to sort of eliminate the ambiguity. So the problem that we actually work with is a problem of minimizing this function G of W, where W is this matrix variable here. Okay, so it turns out that for a lot of interesting matrix problems, there was this nice paper by our colleagues at Colorado School of Mines in 2017, where they showed that for a wide class of matrix problems, this function G of W had some nice properties. Namely, any W, any variable W, lay in at least one of these three different spaces. The first space is one where the gradient is large. The second one is one where the Hessian has a distinctly negative eigenvalue, less than minus gamma, where gamma is some constant bounded away from zero. So that's the second property that W might have. And the third property that it might have is this property here, which is a little bit more complicated to explain in words, but it's a nice kind of regularity property where, you know, if this property is true, it's a guarantee that steepest descent is going to converge rapidly. That's, you know, that's basically what you can say about that. So for this class of problems, it's more general than just being a general non-convex optimization problem. It's got this additional property that any variable W is going to lie in at least one of these three neighborhoods. And the thing is that in each of those neighborhoods, you can do something nice. You can take a step that's appropriate to each of those neighborhoods. It's guaranteed to give you a nice solid amount of decrease in the objective. And from that, you can go to sort of putting nice upper bounds on the complexity. So before I get to that, just a little mention about what people have done in this space, including people on this call, I think, have worked on these kinds of problems. One approach to solving these kind of matrix problems is to use some sort of special initialization, where you sort of gather enough samples to put yourself into a region of the global solution from within which gradient descent will converge reliably. So often you have to do something expensive as a first step, like, you know, compute an approximate singular value decomposition. But once you do that, you can do gradient descent and then get rapid conversion. So that's one approach that's been used. Another one is to use non-convex optimization approaches that make use of knowledge like what is the strict saddle parameter. So if you know what this gamma is, if you know something about this strict saddle parameter, you can design an algorithm based on that knowledge, and you can prove a very nice complexity result, namely that the dependence on the number of iterations is only logarithmic in the tolerances rather than being depending on a negative exponential of the tolerances. So we wanted to design a method where you didn't assume that you knew these strict saddle parameters in advance. So that's kind of the novelty in our method, is we make adaptive choices of these parameters, alpha, beta, gamma, and rho, and so on, that show up in this decomposition of the space. And so our method sort of maintains an estimate of gamma. It maintains estimates of alpha and beta. It sort of makes decisions about which region you lie in based on these estimates. It takes an appropriate step. It's either going to be a negative gradient step or a negative curvature step. And essentially what we show, this is the method which I'm not going to try to explain, but essentially what we show is that, you know, either if you take a negative gradient step or a negative curvature step, you're able to prove that you get a nice amount of improvement in G. If you think you're in this region where steepest descent is converging rapidly, and it turns out you're not converging very rapidly, that's kind of evidence that your estimate of gamma is wrong. And so you just halve it and continue iterating. So there's a lot of bells and whistles in this approach, but essentially what you show is that you can always get, by making a reasonable guess about which part of the space you're in, you can always get a pretty large decrease in the function. All right, so I think I'll skip this slide. But essentially what we end up showing is that even without knowledge of these strict saddle parameters, we show that you can get this logarithmic dependence of the complexity on epsilon g and epsilon h. And of course, that's radically better than the negative polynomial dependence that you get for the general approach. There's also a dependence, by the way, on the strict saddle parameter itself. So if this parameter gamma here is very small, you know, that doesn't bode well for the complexity, but we're assuming that epsilon is independent of that. Okay, so let's move on. I guess I've got about 10 minutes left, Max. So let me talk about what we can do in the case of non-negative bounds. So our first thing to notice here is that life is a bit more complicated, because right up front, the first and second order conditions get quite a bit more complicated as soon as you introduce inequality constraints. So when it comes to first order conditions, it's not too bad. The first order conditions, you can actually write them down in a very compact way by just saying that x needs to be non-negative, the gradient of f of x needs to be non-negative, and those two vectors need to be complementary. You can sort of break that down by classifying the components of x into three classes. You can have a set where an active set where the xi is at the boundary but the gradient's positive, an inactive set where the xi is strictly positive and the gradient 0. But you can also have these degenerate indices where both the xi and the gradient are 0. And that's the thing that makes life a bit unpleasant, are these degenerate indices. And the reason for that is that the second order conditions, the best second order conditions, are the ones that sort of guarantee you that along all directions v that sort of move into the feasible orthant from your current point x star, you'd like to guarantee that the Hessian is positive definite along all those directions, or positive semi-definite. And as soon as you've got degenerate indices, this S2 is no longer a subspace. It now becomes sort of an intersection of a subspace and an orthant. And so checking this second order necessary condition becomes equivalent to checking copositivity of the Hessian. And that's known to be a hard problem. So, just checking that you're at an approximate second order point immediately becomes difficult. So we sort of take the standard cop-out, which is not to try to look for a point satisfying these conditions, but to simply look for one where the reduced Hessian corresponding to the inactive indices is itself positive semi-definite. So our first attempt at this, which has been published in the IMA Journal on Numerical Analysis, this is again work of Mike O'Neill. It sort of seeks an approximate first and second order point, and I think I'll skim over this one pretty quickly for reasons of time. But we based our method on writing down a log barrier function where we sort of capture the non-negativity constraints by just simply using a log barrier. But instead of using a variable for the log barrier coefficient or log barrier parameter, we simply fix that to be the tolerance that we were looking for. So we defined the mu to be just epsilon over 4. And then we sort of took this thing and treated it as an unconstrained problem and applied our unconstrained line search Newton CG to this problem. Okay, so we just leverage what we've done in the unconstrained setting. Now, there's two issues here that we had to sort of seriously deal with to make this work. The first issue is that you can never let these x's go to 0 or go negative. So right away, you sort of have to clip the line search to make sure that you stay in the strictly positive orthant. So that's one modification we had to make. The second modification is that when you get close to a solution, the Hessian of this barrier function becomes extremely ill-conditioned. And so if you start applying the conjugate gradient to the Hessian of this, in fact, I've written it down here on the second slide, if you start applying the conjugate gradient to the Hessian of the barrier function, the presence of these x to the minus 2 terms, that is, some of these x's are going to 0, you start to get, conjugate gradient applied to a very ill-conditioned problem is going to start taking way too many iterations. And so we have to deal with both of those things. And we deal with the positivity issue just by making sure that you don't step more than a fraction of beta of the distance to the boundary. So that's pretty easy to deal with. And those of you that know about interior point methods for linear programming, this is exactly the kind of technique that you use there to truncate the step length. And the second thing is in order to deal with this ill conditioning issue, we scale the Hessian so that essentially goes away. That issue essentially goes away. So we scale the Hessian by taking a diagonal of a modified form of x. And that way we make sure that we're always dealing with a reasonably well-conditioned Hessian. So what we end up with is basically we get something like the epsilon to the 7/4 result that we got for the unconstrained case. There's a little bit of a hitch here, and it sort of seems to be an unavoidable consequence of using the log barrier framework, is that we also get this order n to epsilon to the minus 3/4 term showing up. And that seems to be because we can't guarantee a priori that the iterates xk are not going to wander off to infinity. If we can assume that that doesn't happen, we get basically the same complexity as in the unconstrained case. But we sort of have to wrestle with the fact that that might happen. We can show that it doesn't happen too rapidly. In other words, that the rate of inflation of the xk's isn't too rapid. So we can still prove a reasonable result, but it's not quite as strong as a result we get for the unconstrained case. So that's what I'll say about that. The details are a little bit messy, so I'll skip over that. But recently we've got sort of a different take on this unconstrained problem, and that is to use something that again is closer to what's been done in practice. I've got my eye on the clock here, so I know I'm down to the last 5 minutes. And this is a projected Newton CG approach, and this is basically what we do is at any point x, we sort of we split the variables into the components of x into two sets. One of the ones that seem to be active, the ones that are within epsilon to the 1/2 of the boundary, and the other ones are the ones that seem to be free. That is, the greater than epsilon to the -1/2 or to the 1/2. And essentially, we look for a point that satisfies approximate first and second order conditions defined in this way. And the approach is very simple. First of all, if you look at the free components of the gradient, they should be 0 at the solution. So if they're bigger than epsilon, we take a modified Newton step just in those free components. Okay, so that's the first kind of step we take. The second kind of step we take is that if the free components of the gradient are small, but some of the ones for which some of the active ones, some of the ones that are close to the bound, have a gradient component that's too negative, then we just take a projected negative gradient step. We just move in the negative gradient projection and project back onto the positive orthant. Otherwise, if neither of those things is true, we use randomized Lanchos to find a negative curvature direction on a scaled version of the entire Hessian, on all n of the components. So that's how we get our search direction. For all those kinds of directions, we sort of search along a projected gradient path. We do backtracking along a projected gradient path. So what we can do about this is we can actually recover the same sorts of guarantees that we get on the iteration complexity and the operation complexity as we get for the unconstrained case. The only thing that's weaker than the unconstrained case is that we've got a slightly weaker condition on one of the first order conditions than we'd really like. Here, instead of having an epsilon, I've got an epsilon to the 3/4. And that's the thing that makes this not a completely satisfactory result. This seems to be the price we pay in going from the unconstrained case to the bound constrained case. We have a slightly weak condition on the gradient guarantee for the negative components. So I guess I'm sort of out of time. I'll just say that what we've done in the equality constrained case is to implement a proximal augmented Lagrangian framework. So those of you that know about constraint optimization will recognize these as being sort of first order conditions for equality constraint optimization. These are the classical second order conditions on the Hessian of the Lagrangian in the null space of the constraint Jacobian. The approach we use here, again, we sort of build on what we did in the unconstrained case. We write down an augmented Lagrangian and we add a prox term at each iteration. We don't require the prox term to make this thing completely convex. We allow non-convex subproblems because we're going to use our unconstrained line search method to solve the subproblems. But we can end up proving things about the total number of outer iterations, the total number of inner iterations that you need to solve this subproblem, and the total number of operations, that is the number of gradient evaluations and Hessian vector products. And we've got some complexity results in that space, which I won't go over. I'll just point out that we can prove stronger things when you've got linear constraints and when you've got non-linear constraints. When you've got non-linear constraints, unfortunately, they show up in the Hessian of Lagrangian, and they can create some sort of nasty ill conditioning in that Hessian. So we only get weaker complexity guarantees when we've got non-linear constraints. And I'll finally say that there's actually been a lot of work done in this area of complexity guarantees for non-convex constrained problems in the last 10 years or so. Most of these are in more limited settings. So most of these papers they either just get approximate first order conditions rather than second order. They only look at iteration complexities rather than operation complexities. They only look at linear constraints, various restrictions like that. but there's been quite a lot of work in this space by some of the authors on this slide. So let me just wrap up, and thank you very much for sticking with me for all this time. But I just want to wrap up by saying I think we've been able to show that for a number of methods that are sort of very close to being practical methods for large-scale problems, we've been able to tweak them enough that we've been able to prove interesting worst-case complexity results. And I'll say there's still quite a bit of work to do in this space, particularly surrounding things like primal dual anterior point methods, which have turned out to be very useful for general constraint optimization. It seems to be hard to prove things about worst-case complexity for those cases. And some of these methods that are not so practical that have been proposed, I wouldn't give up on them. That it may be that some of those methods actually do turn out with some smart implementation to be practical. So thanks very much again, everyone, and again, thanks for sticking with me.
Awesome. Great. So for those who do have to go to another appointment, feel free to drop. But I want to take some time to answer some, or have you ask some questions before I jump in.
I've got the gallery format up so I can see more people now. There's Mike Todd. Hi, Mike.
Sorry.
Mike's on. Good to see you.
Yeah. Ditto.
And David, I'll see you tomorrow, I know. And Katja, hi, Katja.
Hi, sorry, I'm just in this weird places. That's why I'm keeping most.
Yeah, you're
camera off.
truncated. We can only see you from the eyes up.
Oh, yeah. Well, I'm in a very strange, accommodations at the moment. So
Right.
there's no normal tables or anything.
I talked to Oktay earlier, so he explained it was
Right.
an Airbnb.
Right. Yeah, exactly.
Steve, one question I have. So in simulation, sometimes we can use computational differentiation to get first derivatives that are unbiased. But when we try to do that for second derivatives, we run into those discontinuities that you and I talked about earlier today.
Right.
The second derivative information is usually pretty poor. Can you do much here when you don't have that direct second derivative information?
No, this really depends strongly on smoothness, I would say. So if you don't have access to second derivative information, that's going to change a lot of things about this. I mean, you could go back to those methods that I mentioned in passing earlier on, that by the Michael Jordan and his collaborators, where they only use gradients, but they occasionally inject noise as a way of escaping from saddle points. And they can end up with second order guarantees, because if you inject a noise and end up going back to the same point, that's kind of an indication that that point really is a local minimum. So they do end up with a kind of second order guarantee, even though they're only using first derivative information. So that might be a better lead for what you're doing than what I'm doing, which is really exploiting the smoothness of the Hessian.
Yeah, thank you.
Steve, maybe I could ask a question. So, I mean, there's sort of a more modest version of your final question on your last slide. So, I mean, I'm trying to reverse engineer some of your thought processes in designing these algorithms. And some of what you seem to be doing is, taking something that is a reasonably practical algorithm and then tweaking it or sort of doing quite substantial work on it to give it a plausible complexity analysis. And I'm wondering whether you see instances where that actually improves the practical performance of the algorithm.
Yeah, that's a good question. We did seem to come across some things like that on certain problems, like particularly from robust statistics. There's this Tukey byweight function, which is a way of regularizing things that is not least squares anymore, but it's least squares where it sort of flattens out. And you can set up problems in that space that seem to have a lot of points that are sort of near the saddle points. And we found that some of our methods did seem to behave better than some of the classical alternatives, because they occasionally would sort of explicitly look for a negative curvature direction to get away from those saddle points. But I would say in general that, the best we could do were, in general problems, like I showed you these Moray-Dolan plots, the best we could say was that at least it didn't really make things worse, which is not a resounding argument, but
It's
at least
reassuring.
it's saying you're not interfering with by adding these tweaks, you're not interfering too much with the practical properties. So, but yeah, I think there are some specialized problems where having those properties might actually help.
I think actually, even for primal dual interior point methods for nice problems like linear programming, the practical algorithms give up the polynomial guarantees, and similar to what you were saying, Kojima and some of his co-authors managed to put back those convergence guarantees, and again, as in your diagrams here, didn't lose too much. But it's very nice to see these practical algorithms actually modified in a sort of conservative but cautious way, so that they still work well.
Right. Yeah. I mean, it was one of the remarkable developments in primal dual interior point methods was that the theory and practice actually came pretty close in the end. Right. I mean, in practice, you sort of implement these step length to boundary rules and so on, which aren't that well supported by the theory, but they're not too far apart. And if you just code up an infeasible interior point long step type method, it's actually not too bad. It's not going to like beat Mosek or anything, but it's not terrible.
Yep.
I had a quick question, Steve, on the matrix problems. So in that set of examples, were you assuming any statistical model on on how the data was generated?
Yeah, I'm sorry I can't answer that rigorously, but I'd have to go back and look at our source paper. Essentially, we based everything quite strongly on this paper here, which I'll send you the deck so you can see the reference. And they seem to have, I'm sure there are problems in this space where it doesn't have these properties. You can probably choose it in some adversarial way that will confound this. So there probably is some sort of statistical distribution that we're assuming, or some sort of niceness property. Something akin to restricted isometry or something like that.
And your algorithm operated just on these assumptions 1, 2, and 3, or was anything specific to the matrix setting?
We just took this as a starting point. We took as a starting point that you could carve up the space W so that any W would satisfy at least one of these 3 properties.
Right.
So that basically was what we took out of that paper, and designed the algorithm accordingly.
Okay. Interesting.
Yeah, it's pretty messy, but you sort of guess that you're in the local phase, and you try stepping, and if you're not converging, then you figure that your parameter guess must have been wrong, and so you adjust that and take one of the other kinds of steps and so on. Yeah. So in spirit, it's not too bad, but it is a bit messy to analyze.
Yeah. No, I'm just really curious because I have similar things where you have these regularity constants and these types of problems, and
right.
You seem to be seeing them pretty well.
It's good not to have to guess those things, to have the algorithm kind of figure those out adaptively. But I recommend looking at that paper because it might give you some ideas.
Okay. Cool. Any other questions?
I'd just like to suggest that instead of minimizing iterations or operations, you could minimize if-else statements in the algorithm. There are a whole bunch of things where you say, if the gradient's this, or if this, and it would be nice to have a sort of unified model that would interpolate between steepest descent and negative curvature and so forth. and maybe avoid these assumptions on the comparison between epsilon G and epsilon H and so forth.
Yeah. That's a good point. So I guess that goes back to something when I started working in Turing point methods 25 years ago. My first algorithms had these so-called fast steps and safe steps, right? So that was kind of an if-then thing. Whereas, the idea of using ascending parameter basically allowed you to combine those two things in a single step, right? So, rather than having a predictor corrector, you were able to sort of glue the two things together, right? So it's the same sort of spirit you're suggesting here, I think.
Yep.
Yeah, no, that's a good point.
I mean, if you're trying to sell automatic differentiation too, it would make it more amenable to automatic differentiation too, right? So
yeah, at the algorithmic level, yeah.
Right.
Yeah, that's an area that's become very hot again because of neural nets, right? So apparently there's a big market for Grievang's book in the Silicon Valley community because they figure out they're doing backprop on neural nets as basically implementation of the reverse mode.
Cool. Thanks so much for coming out, Steve. I guess you have another full day of meetings tomorrow.
But I think it's half a day.
Okay.
I'm not done today. I got a committee meeting in 2 minutes time.
Okay.
So sorry I won't be able to join you for dinner.
Yeah, us too.
But
we'll drink a toast, Steve, and I'll see you tomorrow.
yes, great. I look forward to it. Thank you all again.
Yes. No, thank you for coming and giving a talk.
Yeah. Okay. See you all soon.
All right. Bye.
Bye.